Hello. Let's talk about the electromagnetic spectrum. The electromagnetic spectrum represents all energy waves that could possibly exist in the universe. And you can see they're organized on this page. And in this organization, we have them listed by frequency, which are the top numbers along the page, and also their corresponding wavelengths. Since all energy waves travel at the same exact speed, they all travel at c. We call that the speed of light, and that's 3 times 10 to the 8th meters per second. We can use that and the wave equation to calculate velocity is wavelength times frequency. Well, with a wave equation, velocity again is c, is wavelength times frequency, and that c is 3 times 10 to the 8th meters per second is wavelength times frequency. And why I'm showing you this is the following. The wavelength and the frequency must always multiply to equal this number. So that number must remain constant. So if that's the case, if frequency were to go upward, to get this same number, wavelength has to go downward. By the way, that little symbol there, it looks like a little upside down Y, that's a wavelength symbol. Other books use other symbols, but that's what I'm used to. Same thing with frequency. Other books may use a different symbol for frequency, but I'm just going to use F. The point being, since the multiplication of these two numbers must always equal the same value no matter what, as I was saying, if frequency goes up, wavelength needs to go down. And this is getting a little messy, so I'm going to erase all this stuff here and we'll go over it again. So C is wavelength times frequency. And again, this C value is always the same value. And if frequency were to go down, in order to keep this value the same, then wavelength would have to go upward. To show you a very simple example on the side, say something always had to be equal to 12. X times Y always had to equal 12. Well, we could do 1 times 12, and that would equal 12. Well, what if we didn't do 1 times 12? What if we said 3 for X? Well, 3 times what? Well, 3 times 4 would be 12. What if I said 6 for X? Well, if 6 were X, then Y would have to be 2. So what's happening is, as X goes upward, the Y value has to go downward and downward, so that we always enter, so that will always be 12. So that's the same thing for waves. If frequency goes up, wavelength goes down. If frequency goes down, wavelength goes up. Well, look what happens here as I go from this way across this chart, which I know is against the grain in terms of the way you read things. But as we go from what we call radio waves all the way to gamma rays, as we move this way, notice that the frequency is going up. So frequency is going up. And that means as I go this way, as the frequency is going up top, the wavelength, you can see, is getting smaller. And that makes sense, because no matter what wave I'm talking about, whether they be radio waves or microwaves or gamma rays, the speed of those waves always travels at the speed of light, speed of any energy wave in a vacuum, which is really, really, really fast. And we'll talk about the significance of that number a lot more ways later. But moreover, what I want to do is just show you the general kinds of waves that exist. We have, of course, the first set of waves, and I know I'm going backwards on this chart, but we have radio waves. Radio waves are common. They are, in fact, indeed, what powers your radio at home. And since these are the lowest frequency, they also have what we call low energy. So all the waves on this side, radio waves, are the lowest frequency and lowest energy. They're also the longest waves, meaning they have a very long wavelength. And over on this side, gamma rays, the other side of the table, they have high frequency, and therefore they have high energy. These waves are very energetic. Matter of fact, so energetic that gamma rays are typically associated with nuclear reactions and or the makeup of suns and stars. So these are very energetic and cause lots and lots and lots of damage. But their wavelengths are really, 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 really small wavelengths. Those waves are really squished together, despite the fact that they're high energy. As a matter of fact, I'm going to kind of redraw that again. I'm going to have to kind of go, I'm having a hard time drawing the other way, but the wavelengths, you know, the distance between the one peak of a wave and the next peak of a wave, that's a really small distance, versus these low energetic wavelengths have really long wavelengths. So that's a really long wavelength there between here and here. Now, what I'm going to do in the video is I'm going to go through the different kinds of waves. I'm going to talk about radio waves and show you some examples. Then I'm going to show you about microwaves, infrared, visible spectrum, which, by the way, you'll note gets a special kind of section here where it's a little expanded. We'll talk about UV or ultraviolet, X-rays, and gamma rays. So let's talk about those, and we'll come back to this. All right, we'll be right there. Radio waves. Radio waves are all around you right now. They come from the radio towers, typically from the radio stations in our area. That would be from Philadelphia. That energy travels from there to here, and it's in the air all around you. In order to listen, you need to turn on a radio receiver, make sure the antenna is up and ready to prepare to listen, and turn on your favorite station. Microwaves. Microwaves are another low energy, although slightly more energetic than radio waves. They're used for your phone to communicate with the cell towers, so you can send those texts and look at those apps. Infrared waves. Some of you are familiar with thermal imaging. You have or may have seen it in video games or movies or shows where you can detect heat energy. That's infrared. And it will sometimes be coded to show red being hot and blue-green being cold. A lot of remote controls use infrared, are IR bulbs. And here I have an IR bulb, and if I press the button, I'm pressing the button, you're not seeing much, not doing anything, not doing anything, not doing anything. But certain digital cameras, like the one on my computer, which is here, if I bring the remote control in front of the camera, and you can see how I have the image of it in the computer screen. If I press the bulb in the background, you'll note that it lights up. So that's the computer camera showing it. I'll lift this up, show you how I'm doing this. There we go. You can see the IR light as translated by the computer camera. Doesn't work so much for this camera, but works for that one.
visible light. We're going to illustrate that with this light bulb. Right now it's not lit up, and right now, or when I plug it in, it gives us white light. And white light is all the colors of the rainbow. I can break that white light into components via a prism. I have here a little screen or fraction grating, and what I can do is I can put it up to the camera, and when I put it up to the camera, you will notice that the white light is broken up into its components of the rainbow. I can remove that, and you can see all the wonderful colors of the rainbow, and I can move this grating, and you can see those colors of the rainbow. So you can see clearly Roy G. Biv being fleshed out there in all kinds of a starburst pattern. Okay. There are some visible light sources which only give us one of the colors of the rainbow, or just even one sliver of a color of a rainbow, specific wavelengths of light. Lasers do such a thing. So when I have this laser here, I can use it, and I have a red laser. And when I put that on a desk, you can see that it is a specific color of red. That's only one wavelength of red light being shown. There's other special things about a laser, which we'll get into, or you may get into other days, or you can look up on your own.
Ultraviolet light is most familiar from the sun, UV rays. UV rays are what can give you sunburn, so make sure that you use sunscreen, like I do, to make sure I don't burn my forehead. We've been increasing in energy as we've been going through this video, so now we're to X-rays, which have even higher energy, higher frequency, so much energy that they can penetrate through your flesh, but yet get stopped by your bones to give you X-ray images. The last stop on the tour of the electromagnetic spectrum is gamma radiation, or gamma rays, typically found in stars or nuclear explosions. The gamma rays have the highest amount of energy of any of the types of electromagnetic energies, and that is why it is the most damaging to you and me. So hopefully you are not exposed to these kinds of energy. All right, so I just want to go and stop back at the visible light spectrum. You can see that the visible light spectrum is pretty much the cutoff between waves and rays that don't harm us to rays that possibly do harm us. UV can give us sunburn and skin cancer. X-rays, if we're exposed to X-rays a lot, they will basically, in overtime, cook your insides and give you all kinds of problems, including cancers. Having an X-ray once in a while isn't a bad thing, but if you were an X-ray tech being exposed to X-rays every day, if you did not step out of the room, you would create and have some problems. And obviously gamma rays, you don't want to hang out on a surface of a sun or around a nuclear explosion. That would be bad. But all these waves over on the opposite side, infrared microwaves and radio waves, they are of no harm to us because they're lower energy. Within the visible spectrum itself, which is just a very small part of the overall electromagnetic spectrum. That's why it has this special cutout. Red waves, red light, are your low frequency visible light. It's low energy. And your higher frequency are your blues and violets. They give you the higher transmission of data when you have something like a Blu-ray player versus an old-fashioned red laser DVD or CD player. So that's a good portion of the electromagnetic spectrum. I hope this tour was a little helpful in getting you to be comfortable with these types of energies.